All right, so let's just take a look at our standing wave on a string logic. Okay, so I'll put up right here. So if you had lab yesterday morning, you got to see what a standing wave on a string looks like up close and personal. And what you noticed, or if you've just read the lab for the Friday session later this week, what you've noticed is that you're asked to measure the distance between nodes. So just to backtrack just a bit, this slide here. So nodes are locations where the amplitude of the standing wave is equal to 0. Antinodes are the opposite. Now the amplitude of the standing wave is a maximum. And when you're collecting data in the lab, you're going to measure the distance between adjacent nodes. And that has to do with the fact that a standing wave on a string can only break down into half wavelength multiples or intervals. So you can have an m is equal to, let's say, 5 standing wave, except there will always be a greater number or one greater number of nodes than antinodes. And there's no scenario where you will have like a quarter wavelength or a third of a wavelength. It's always halves. And that is also how standing waves in certain tubes work. We talked about closed, closed, open, open, and then open, closed, or one of each. Anytime the ends of a tube match, the standing wave that will form in that tube is going to be a half wavelength. So for the case of closed, closed, or I should just say in general, anytime there's a closed end on a tube, a node is going to form there. So for the closed, closed tube, you have 2 nodes, 1 antinode. And M here also refers to the number of antinodes, just like it did for the standing wave on a string. So if we can figure out what V over 2L is for this particular tube of length L that's got air of a certain temperature inside, then we can predict pretty easily what any higher level or higher order standing wave frequency will be. Now for open, open, the difference is that since you don't have a blocked end on either side, the an antinode is going to form on the open end. So for the m is equal to 1 standing wave, you've got 1 node that forms at the halfway point, and then 2 antinodes. And in this case here, the m value that is relevant is the number of nodes as opposed to the antinodes. And then finally, for closed open, we know to expect 1 node on the blocked side, 1 antinode on the open side, but that means that you can't capture a complete half wavelength inside of this tube. It's just going to be forced to be a quarter. Think about what we would have to do if we wanted to capture 1 complete lobe, just to kind of use this term, for the m is equal to 1 standing wave. So in other words, if we look at this displacement curve, we've got a node on this side, an antinode on that side. This tube would have to be twice as long just to hold 1/2 wavelength, like we saw with the closed, closed tube. So the difference here is that lambda is going to be 4 times L over M. That's going to result in or explain why there's a 4 in the denominator here. And then another difference, for a standing wave in a tube that has mismatched sides, the even numbered modes simply can't form. So we have 1, 3, 5, 7, and so on. So if we're counting the number of nodes, which is the rule for a closed open tube, we would just legitimately skip the even values. So for m is equal to 1, we've got a single node on the blocked side. For m is equal to 2, we've got 2 nodes, but we would say 1, 3, or excuse me, I think I said m is equal to 2. For the next highest possible standing wave, you would have 2 nodes, so 1 and 2, but we would count 1, 3, skip over the 2. And then for 5, we have 1, 3, 5. The open end of the tube is always going to be where you are guaranteed to find that quarter wavelength. For m is equal to 1, the entire space is a quarter wavelength, so that's kind of a a special case, but when you look at m is equal to 3 and 5, I've got a complete half wavelength and then a little extra, and then 2 complete half wavelengths and a little extra. So that's where the quarter wavelength is going to show up. So we've got some example problems, 2 back to back, and then we're going to move on to the second half of the chapter. So this first one is a standing wave in a tube with 2 open ends. We have some knowledge about the 2 adjacent frequencies that can produce standing waves. We want to figure out what the second harmonic standing wave, we want to figure out the frequency of the second harmonic standing wave. And then we're going to do something similar for a blocked or a closed open tube. So let me quit sharing here. I'm going to jump over to OneNote on this side, and we can start solving those. Six. Okay. Okay, so let's share on this side. OneNote. Okay, so let's switch to the appropriate class. We're 252.17. Let me make sure that you are, yeah, okay. So 17.3 is where we need to pick up. So we have an open tube. There's no information about the temperature of the air. So that in that scenario, it's always safe to assume that we're talking about room temperature air. So that V would be 343 meters per second. We've got 2 possible standing wave frequencies, one at 300 hertz, another at 400 hertz, but no standing wave frequencies in between. And we want to figure out what F sub 2 is. So we have, let me see real quick. Okay, so actually we can get around needing to know what L is here because we know what 2 adjacent standing wave frequencies are. So I'm just going to say F sub n is equal to 300 hertz. And F sub n plus 1 is equal to 400 hertz. I'm using an n here as opposed to an m, just so that we can figure out what the fundamental frequency is, and then we can solve what the question's actually asking us for F sub m, where m is equal to 2. So we saw in Monday morning's lecture that the allowed frequencies that can form on a specific string, or in this case, a specific tube, they form a series. So if we know that these 2 frequencies are the only allowed, or the 2 adjacent allowed frequencies that show up in this series, delta F is just going to be the difference between these. So F n plus 1 minus Fn. This is going to give us 100 hertz. So the takeaway here is that F1 is 100 hertz. So knowing that, we can go right to this expression here. F2 is equal to 2 times V over 2L. And the V over 2L, this is just another way of expressing F1. So all we need to do here is take 2 times 100 hertz. F2 is 200 hertz. And we weren't really given explicit information about which M values match up with 300 and 400 hertz, but we can see here that this 300 hertz wave, standing wave is going to have to be F is equal to 3. The 400 is going to have to be M is equal to 3. And then the 400 is going to be M is equal to 4. So in other words, F1 we know is 100 hertz. Therefore, F2 is going to be 200. That's what we solved for. F3 was one of the given values. It's 300. F4, another given value, is 400 hertz. And for a standing wave in a tube that has ends that match, it's just as simple as that. It's very, very similar to what we discussed as it related to standing waves on a string in our last lecture. The next question here gets a little bit more complicated, or we have to consider something else important. So we've got a closed open tube of air. There are standing waves at 245 hertz and 315 hertz. So let's start with the same assumption here. F sub n is going to be 245. And then F sub n plus 1, the next highest allowed standing wave, is 315. So there are no frequencies between these two. We're looking for the third harmonic standing wave. So not M3, let's just say F3. That's our unknown. So let's start this procedure similar to the way that we did the other one, but I'm going to point out a specific difference that we have to kind of pay attention to. So let's see, how do I want to do this? Let's figure out what delta F is for these two adjacent standing wave frequencies. So we've got 315 hertz minus 245 hertz. So that is 70, right? Let me double check though. 315 minus 245, yeah, 70 hertz. So the allowed standing wave frequencies are separated by 70 hertz. But keep in mind here, for closed open, even numbered M do not exist. So the separation between these two allowed standing wave frequencies is not the fundamental frequency. What we would need to do in order to figure out what that is take the 70 hertz and then chop it in half. So therefore, 70 hertz cut in half is going to be F1, so that's going to be 35 hertz. So we are concerned with the M is equal to 3 standing wave. So F3 is going to be 3 times V over 4L, where we just determined that V over 4L is 35 hertz. F3 is 3 times 35 hertz. That's going to give us 105. Yeah, so 105 hertz for F3. And just to kind of finish this one out the same way that we did with our open tube, we can figure out which M values we were given for the adjacent standing waves. So F1 we've determined is 35. F3 is the next allowed one. So that's going to be 3 times 35, 105 hertz. The next allowed will be F5. So that's 175. Next, F7 is going to be 245. So this is one of the given values that we started off knowing. So this tells us by default that F9 is going to be 315. And that's doing a little bit more than what the question asked us, but it is, I think, just worth it to see specifically in detail how these closed open tube standing wave problems differ from the either open open or closed closed. There's a problem in our standing waves lab that is going to ask us to compare scenarios that are essentially similar to example 4 and example 3, just to kind of add all the possible information to this problem before you blink back over. The m is equal to 3 standing wave in this tube would have one complete half wavelength and then a quarter wavelength here. So let me, the node that's on the blocked side would be 1, and then the second node that shows up tells us that this would be m is equal to 3. And for the open tube, we were looking for an m is equal to 2 standing wave. So that means 2 nodes, and they would have to form kind of like this, so that we've got one complete half wavelength in the middle. So this would be lambda over 2 between here and here. Then you've got lambda over 4 between here and here, and another quarter wavelength on this side. Let's do more like this. Over 4 between there and there. So when you add this up, you have one complete wavelength that is contained inside the open tube. And then here we've got a quarter wavelength over here, and then a half wavelength. So the absence of that other quarter wavelength on the opposite side kind of hammers home why the even m values just can't form in a tube that looks like this one. Okay, so those 2 problems mark the end of the first half of this chapter. Are there any questions before I switch back over to our normal class notes? Okay, jump in at any time if you do have questions. Quit on this end. And sign out here. Okay, so superposition part 2. So just to kind of recap here, we spent some time walking through all of the possible ways that a wave that is propagating down a string and as such is being forced to interact with itself. We stepped through all the possible ways that we could sum up the displacement, like the net displacement of the wave that's traveling toward the right, so the red one in this case, and then the green one that's traveling toward the left. And we split this up into eighths of a period so that we could see that there were 2 scenarios that would lead to a standing wave that had a net displacement of 0. The 2 waves would have to be perfectly out of phase. This is kind of similar to what you achieved with the microphone, the 2 microphones in our traveling waves lab. But the difference here was that one of your microphones was further away from the sound source. So the amplitudes of the two waves that you measured didn't match. In this case here, the leftward traveling wave is just literally the rightward traveling wave reflected back on itself. So those amplitudes are going to stay consistent. So for this example here, at 3/8 of one period and 7/8 of one period, if you could take a snapshot of the standing wave, you would be able to catch the string not moving at all, or looking like it's not moving at all. And then on the opposite end of that, we can look at 1/8 of t, and then on the opposite side, 5/8 of t. This is the scenario where the two waves are still propagating in different directions, but they are perfectly in phase with one another. So the red one's at a maximum when the green is, and then the red one's at a minimum when the green is. All the points in between represent points along your standing wave that are neither nodes nor antinodes, but just somewhere in between. So it's an imperfect type of interference in that case. So to relate this to a sound wave, just as we encountered at the beginning of this chapter with the example about two pitching machines that won't let baseballs occupy the same point in space at the same time, but two loudspeakers can allow sound waves to exist at the same point in space at the same time. If we've got two loudspeakers that are separated by some distance that we can measure, we can predict, we should be able to find places where one signal is at a maximum amplitude, the other one is at a minimum amplitude, so they add together to 0. That's the case of destructive interference here on the the right-hand side. And then for the case on the left, if you have a different spacing, so an integer multiple of the wavelength of the source or the signal that these two loudspeakers are producing, then you can catch wave 1 at a maximum at the same time wave 2 is at a maximum, and you end up with a displacement, a net displacement that is equal to twice whatever the amplitude of either of the individual waves is. So in other words, we are using a lowercase a in this context to represent the amplitude of just one of these signals, so that when they add together, the greatest possible value they can have is 2 times lowercase a. Keep in mind that we also encountered lowercase a when we were talking about power and intensity. It referred to the surface area of a sphere. Here, this is just our reminder that the total or the maximum amplitude would be capital A in this context. So we have 2 lowercase a's that we can add together to achieve that. But what I want you to pay attention to are the terms constructive interference and destructive interference. So in our previous chapter, we learned how to write displacement functions for each of these individual waves. We have, again, our amplitude lowercase a for wave 1. It's going to be sine kx minus omega t plus phi naught. But in this case here, we are tracking 2 different, or our goal is to add together 2 different sound waves. So we have to tell the difference between x1 and x2 in this next term. But keep in mind, omega has to be the same for both of these. We're assuming that the 2 loudspeakers are sending out exactly the same signal. So at the same frequency, it's traveling at the same speed, all of that. And then over here, we have our k sub x2 with exactly the same omega, but there are phase constants that are different. So since we're not just talking about a single displacement function, but 2, instead of just a phi naught or a phi 0, we have phi 1, 0 for the first wave, phi 2, 0 for the second wave. And I want to point out here that the waves that we're talking about in this case are traveling in the same direction. So the omega t terms are going to be subtracted for each one of these. That's another way of saying that we made the assumption that we're talking about 2 waves that are propagating in the positive direction. But if we had 2 waves that were propagating in the negative direction, we would have plus omega t's in each case. So since these 2 waves have so many commonalities, we can collapse, or we can simplify this displacement function into the sum of 2 terms, where we're treating everything that's inside of the sine function as just phi sub 1 and phi 2 in this case. So the phase, not the phase constant, or not the phase difference. And since the phase difference is delta phi, oh, I didn't. Okay, so let me back up here. So the phase difference between these 2 sources, delta phi naught, I can take phi 2, 0 minus phi 1, 0. And then the information at the top of this slide is just a repeat from the previous one. So if we combine those two expressions and make use of a trig identity down here at the bottom, we can collect all of the stuff that is common to the two waves and separate it from all the stuff that is specific to each wave. So the 2a cosine and then this delta phi over 2. Since I'm comparing two waves to one another, delta phi is just going to be a value that will apply equally to wave 1 and wave 2. So we can pull that out front. Then we have sine k. K is going to be the same for both. Omega is going to be the same for both. T is going to be the same for both because we're still working under the assumption that we're looking at two snapshot graphs that pertain to just one point in time, but the same point in time. So T is equal to 0 for both waves that are propagating, let's say, toward, I guess for you, this would be toward the right. So we have an X average and a phi naught average. And if you're wondering where this cosine came from, it's from this, this trig identity down here at the bottom. So obviously there's a lot of algebra that we skipped from the top rectangle to the second one, but this is the justification or the logic for introducing the cosine of this half angle, essentially. So this is a repeat, again, of the last new thing that was mentioned on the previous slide. We demonstrated a bit earlier, a couple of slides earlier, we saw that if you took your two loudspeakers and set them so that they were an integer multiple of lambda apart, we would catch the maximum possible combined amplitude. So in other words, when this phase difference is some integer multiple of 2 pi, you're going to have a 2 in the numerator of this expression inside the square brackets, a 2 in the denominator, and you're going to have a cosine that leads you to either plus or minus 1. So in other words, everything inside of the square brackets is going to be capital A. It's going to be plus or minus 1. When you have a half integer multiple, then that leads to the case where you observe destructive interference as opposed to constructive interference. So you have one signal that is at a maximum when the other one's at a minimum, and this the cosine function here, cosine delta phi over 2, is going to give you a 0. So there's 0 amplitude for the net displacement in that case. So if we take a look at what this would look like, because again, we're talking about three-dimensional sound waves in this scenario, but this is something that we can apply to really any three-dimensional wave. So light waves will interact with each other or interfere with each other in a similar fashion. Imagine we've got two sound sources. We've got our green source and our blue source. They're producing the same signal. So the wave fronts that are emanating away from the blue source have exactly the same wavelength or are separated by exactly the same distance as the ones that are emanating from the green source. And if we look at where these circular wave fronts interact or where they overlap with one another. So anytime a green wave front intersects with a blue one, we know that we're looking at a peak that's matched up with another peak. If we see a point where the halfway points, like the midpoints between adjacent wave fronts, match up, or I should say the midpoints between adjacent green wave fronts match up with the midpoint between adjacent blue wave fronts, then what you have in that case is a trough and a trough that line up. So both of those count as constructive interference. If we have one or the other, so a peak from, let's say, the green signal matched up with a trough from the blue or vice versa, then we have destructive interference, where these are going to add up to 0. And there are red and black dots here that let us kind of mark out antinodal lines or nodal lines. And we'll start with the kind of reddish colored ones up here. If these are crest and crest or trough and trough, then we should expect to find antinodes along this line here. And the black dots, since they are one peak, one trough, they are going to be nodal lines. So I think the term, I'm going to loop back, yeah, so this is kind of what I am kind of leading us toward. We saw a couple of, like a handful of individual places where the peak was where the amplitude, the displacement of one of the waves was either maximum or zero in each case. But we know in real life that we can find sections where, let's say, the amplitude of or we can find locations where the amplitude of the green source's wave might be 3/4 its maximum value. We can pair that up with a place where the blue wave has an amplitude that is 1/4, something that will still add up to the maximum possible amplitude. So we can take those dots from the previous or the earlier slide here and then turn them into continuous lines. And the red lines where you experience maximum constructive interference are antinodal lines. The black ones are nodal lines because you have perfectly destructive interference along that path. So to jump backward and see why this has to be true mathematically, we know that anytime your phase difference is an integer multiple of 2 pi, you're going to end up with the maximum possible net displacement. When it's a half integer multiple, you're going to end up with the minimum possible. So the terms that we can apply to those extremes, I suppose, so not constructive interference where you have two waves that add together as opposed to well, let me phrase it this way. Maximum constructive interference is always going to result in an amplitude that's twice either one of the individual waves by itself. Perfectly destructive is always going to result in an amplitude that is 0 times whatever the individual wave is. But there are values in between there that are kind of adequately explained as being partially constructive interference, but that means that the other part of that interference is destructive interference. So you have like these two extremes, maximum constructive, perfectly destructive, but in between you're getting a little bit of both. It's kind of like what you either did see or will see when you looked at your vibrating string somewhere that wasn't a node or an antinode. You caught something in between. So this delta R is the path length difference. And this next slide identifies or defines this path length concept. So let's see here. Okay, so we've got these curves that represent a connection or like a chain of dots that are all antinodes or a chain of dots that are all nodes. This is a concept that's also going to come into play when we talk about wave optics. So in the chapter that we're going to start as soon as we finish this one here, but we're going to apply it to light as opposed to sound because light is another example of a three-dimensional wave. So this behavior has to be something that we can identify or that we can observe for both sound and light. So we've got our first thought question for this half of our chapter. These two loudspeakers are in phase, so they are producing the same sound wave. They are spaced out. They're spaced out in a way that will lead to constructive interference. So the wavelength of the signal is 1 meter. And imagine that you are the observer here at this dot. You're 8.5 meters away from one of them, 9.5 meters away from the other. So what you experience at that location is going to be a mixture of the signal from loudspeaker 1 and loudspeaker 2. So it's going to be either maximum constructive, perfectly destructive, or somewhere in between. I kind of gave away the answer here because we know that these can infer that these loudspeakers have to be separated by one wavelength, so an integer multiple of lambda being 1, because otherwise the distance between the observer and each loudspeaker would be separated by something other than an integer multiple of lambda. So in other words, the path length difference is what we were evaluating here, that delta R, and that would be 9.5 minus 8.5. You're left with 1. 1 is an integer multiple of the wavelength, so this is maximum constructive. And for a sound wave, this is something that's usually kind of hard to pick out in real life, but what you would experience at this location here is a sound that's a bit louder than you would experience if you found a location of perfectly destructive interference or somewhere in between. Okay, so we pause real quick. Backtrack here. Is there any part of this rationale that you need to see or hear one more time? Okay, let's keep going. So applying this back to the same image that we started off with, our two sources, green and blue, that are producing the same wave, propagating through the same air at the same speed. An antinodal position is going to be one where you catch two peaks or two troughs. And the example here that is labeled capital A is two peaks. But remember, if you can find two midpoints or two troughs, that's also constructive interference. B, on the opposite side, catches the peak of the green signal, but the trough of the blue. So you have destructive interference. And if we look at the separation between, first, we can check the blue source here. If we look at the separation between the blue source and dot A, that's in a full integer multiple. That's also true for dot A and source C, or excuse me, the green source is what I mean to say. And if we look at the point B over here, it's a half integer multiple of wavelengths away from blue, a full integer multiple away from green. And we've got this dot C here that we're going to evaluate in our next thought question, if memory serves. Yeah. So this is exactly the same image that we saw before. How can we characterize the interference at point C? Maximum constructive, destructive but not perfect, constructive but less than maximum, perfect, or none. Take a second to see if you can land on one of these and we'll talk it through like normal. Okay, so the easiest one that we can eliminate is there is no interference at point C. Point C is, we can see the way that the wavefronts are kind of laid out, that both signals or both sources have affected the area of point C. So there is going to be interference of some type. And then the next easiest ones to eliminate are B and C, because imperfect destructive interference is legitimately a synonym for less than maximum constructive interference. So there's no difference between B and C, in other words. So it's either maximum constructive or perfectly destructive. We have a trough of the blue signal, a trough of the green signal. That's going to be maximum constructive, even though both of those midpoints line up with the most negative displacement as opposed to the most positive displacement. The point is that they match, though, so that's maximum constructive no matter what. Okay, so building off of that earlier thought question that we saw pertaining to two loudspeakers that were separated by some distance, we can kind of take a look at the conditions that would match up with an M value that would produce an interference that would still be something that a human ear could detect. So back in the second half of chapter 16, the traveling waves chapter, we saw a span or like a range that represented the lowest frequency that a healthy human ear can pick up and then the highest frequency on the opposite end. And it was about 20 hertz on the low end, about 20,000 hertz on the high end. So if we've got two loudspeakers producing the same sound, they are 0.2 meters away from one another, and you are the observer over here, 4.25 meter away from one of them, 3 3/4 meters away from the other. Your path length difference here would just be 4.25 minus 3.75, so a half meter. So if you were trying to locate all of the minima, so all of the examples of perfectly destructive interference that match with a frequency that a healthy human could hear, you would first look for the half integer multiples of 2 pi. So you want delta phi, the phase difference, to be m plus 1/2 over 2 pi, or excuse me, multiplied by 2 pi. We saw from our definition of the path length difference a few slides earlier that we could say that the wavelength times this phase constant divided by 2 pi is equal to the path length difference. So delta phi is going to, the 2 pi is going to be common to each. The path length difference applies equally to loudspeaker 1 and 2. But now what we're looking for is the minimum wavelength that a person would be able to detect. So minimum wavelength matches up with the largest possible frequency. So we are looking for the frequency that is closest to 20,000 hertz, but doesn't surpass it. And we don't know anything about the wavelength of the sound for this case, but we can count on one, the speed of sound being the same for, or I should say the wave produced by loudspeaker 1 is going to propagate at the same speed as the one produced by loudspeaker 2. And we know that if V is equal to F times lambda, 1 over lambda has got to be F over V. So the minimum wavelength is going to match with the maximum frequency. V sound is going to be a constant. And if we solve these simultaneously for M, we're not going to get something that's an integer. We get 28.65. So that's telling us that the largest possible wavelength, or the largest possible F value for that a human could still hear, would have to be the F28, or the M is equal to 28 wave, not 29, because we fell a little bit short of 29. So kind of like Price is Right rules. You want to get as close as possible, but not go over. So solving these two expressions together gives us this one here. So FM is going to be M plus 1/2 times V sound over the path length difference, where V sound, the path length difference, and the 1/2 are all constants. We plug in the M that we calculated, and the shortest possible wavelength that a healthy human would be able to hear would be the largest possible frequency. So that would be 19,551 hertz. And for the lowest possible, remember, we never start with M is equal to 0, but we start on M is equal to 1. So the lowest possible frequency, which matches up with the longest possible wavelength, would be 1,029 hertz. And the next slide is the same type of question, but now we're looking for the maxima as opposed to the minima. So instead of a half integer multiple of 2 pi, we want a full integer multiple of 2 pi. Our phase constant definition is no different because this is the same physical scenario as before. So we're still looking at two sounds that have the same wavelength. They're propagating at the same speed. The position of the observer is the same, so the path length difference is still going to be delta R. Now, when we solve these simultaneously, instead of a little bit below M is equal to 29, we get a little bit above M is equal to 29. So just as we did before, we can plug in our M value 29 in this expression here. The highest possible frequency, thus lowest possible wavelength that you would be able to detect would be 19,894 hertz. And then the longest possible wavelength and the lowest possible frequency would be 686 hertz. So this is just an extra demonstration that kind of ties us back to the idea of a series representing the frequencies that either match up with an allowed standing wave on a string or in a tube, or in this case here, that match up with the locations where you would expect to find either perfectly constructive interference or perfectly destructive interference. 670 hertz, let's say, would match up with something in between perfectly constructive or excuse me, perfectly destructive or maximum constructive. Okay, we're shifting gears a little bit here to shine some light on something that we actually all observed in the Traveling Waves lab, but I didn't ask you to evaluate in any way. So there were, we have like 8 of those tuning forks that were connected to resonating boxes. A bunch of them have the same frequency, but they're not all identical to one another. So some of you had tuning forks that matched up with about 384 hertz. Some of you had 312 and a half. Some of you had 256. Those were all different notes. And the experiment that we were carrying out last week just involved that we use a microphone to record or to observe how the pressure was varying at that one location. So we were close enough, or our microphones were close enough to the tuning fork resonating box that the signal that we saw on Logger Pro was primarily from our own tuning fork. However, that microphone could hear everything else that was going on in the room. So embedded in that data that you collected was the sound of other people talking, was the sound of, let's say, the HVAC system in the lab that we were working in, and also the sound of the other tuning forks that were different frequencies from yours. They were kind of embedded in there, but we had no problem isolating our own tuning forks frequency. So if we had 2 tuning forks that were not separated by like a large number of hertz, like the 312 and a half and the 256 or the 384, if they were really similar to one another, then what you would be able to observe is an oscillation in the volume, or like the amplitude of the sound that you would pick up. So in other words, you would be able to hear a sound that seemed like it was getting louder, quieter, louder, quieter, louder, quieter. And that's not something that you would have observed if you struck just one tuning fork by itself, if you had 2 tuning forks that were the same frequency, or if you had 2 tuning forks that were very different frequencies. In order for this to be observable, they have to be close but not identical to one another. And what you are observing here, or the term that we use to describe this, is beats. So this signal down here at the bottom would be the combination of 2 tuning forks, one with that have frequencies that are about, maybe a handful of hertz different from one another. And if you collected data for some short time interval, delta t, you would see 2 like distinct behaviors that are overlapping each other. So if we look at the dotted line here, so this like kind of gray dotted line, we can find times where these 2, or the sound waves produced by these 2 tuning forks, are interfering in a way that causes them to add together perfectly. We can see locations where they cancel out perfectly. So in other words, anytime you see plus or minus 2 times A, that's perfectly constructive. Anytime the value is equal to 0, that's perfectly destructive. So it kind of oscillates in between those 2 extremes, pretty much the same way that our standing waves on a string did in this week's lab. But the underlying effect here is represented by this blue curve. So this is not just one tuning fork, but the combination of the 2 of them. So there's an underlying period here that would match up with the average frequency between those 2 tuning forks. So if you had like a 315 and a 317, that average would be 316. And it's modulated. So there's this underlying period, but we can still see that the dotted line that represents the envelope that kind of encloses this behavior here, this is undergoing its own loud, soft, loud modulation. And then the underlying period of the blue wave is going to be whatever the average period of the 2 tuning forks would be. So the way that we count a beat requires that we go from loud, soft, loud. So for example, if we start here at t is equal to 0, 1 beat would be when we get to the next highest peak. So in other words, it's the wavelength of the gray dotted line. So the beat frequency is the number of beats per second. So this is something that you would hear as the combination of these two waves, not just one or the other. That is twice the modulation frequency, which is like the, I guess like the underlying period from the previous example. So the beat frequency is twice the modulation frequency. The modulation frequency, just as any frequency f, we can write that as omega over 2 pi. So in other words, we defined the angular frequency omega as 2 pi times f. So that means that f would be omega over 2 pi. So we have a 2 and a 2 down here in the denominator. However, the modulation frequency is going to be the average of 2 omegas. So imagine taking the the two frequencies, adding them together, and then dividing by 2. We could achieve exactly the same thing by taking the difference between the omegas, divide them by 2 pi, and then divide that by 2. So that's just a long way of saying that the beat frequency is going to be equal to the difference between the two frequencies of the tuning forks that you were using to achieve this. And then down here at the bottom, yeah, so because we're just concerning ourselves with the difference between two frequencies, there's no reason that I couldn't say that F1 is 316 hertz and F2 is 318 hertz, so that the difference between those would be -2. But since a frequency is like a scalar that doesn't really, like a negative frequency doesn't have a meaning really, we're going to always arrange F1 and F2 so that the beat frequency is going to be positive. So F1 is always going to be the higher number frequency, F2 is always going to be the lower one. So for this thought question here, this is exactly the same image that we saw a couple of slides earlier, but let's pretend that this result was the combination of a 610 hertz tuning fork and a second one. And we want to figure out which of the choices here represents the second tuning fork. So we hear 3 beats per second. So that tells us that the separation between our two frequencies is going to be 3 hertz. So 604 is out, 616 is out. We have too few and too many. So either B or C would produce the same thing. So that means it could be a 607 and a 610, or it can be a 610 and a 613. You would hear 3 beats every second for each of those scenarios, because the only thing that matters is the difference between the two frequencies, and we're allowed to change the definition of F1 so that our beat frequency is always a positive value. So in other words, we can go up 3 hertz or down 3 hertz. So either B or C would be correct in this case. Okay, that's a weirdly short second half there. So let's see, today's Wednesday. We have a chapter 7 superposition assignment that's due on Sunday. So since we finished in time, I'm not going to move the homework date earlier, because that would just be pure evil, but we are good to move on to the next chapter, the wave interference chapter. But before I do that, does anyone have questions about anything that we mentioned today that you want to clear up before we jump into the 33rd chapter? Okay, I'm going. Oh, I noticed. Oh, I missed some chat questions here. Okay, so we have one from about 5 minutes ago. If you were to strike 2 identical tuning forks at the same time at a certain distance, would the sound cancel out or no? If you could control the maximum displacement, so like the amplitude of one and the other. So in other words, think back to last week's lab where we had our two microphones set up a known distance away. Because there was just one sound that both were listening to, one of them was going to hear a smaller or quieter sound because it was further away. So if you had two identical tuning forks and you accounted for the fact that the dampening would be different for each microphone, you could come up with a scenario that would cause the sound to cancel out completely. So this is why you never, like if you're at a concert and there are speakers that are placed on different sides of the stage, this is why you would never be able to find a location where there's legitimately no sound, because you would be able to observe the sound from each speaker, whether you were closer to one of them and further away from the other, or vice versa. So there would be the amplitudes wouldn't match. So you wouldn't get to a complete dead spot, but you would be able to find spots that were better suited than others. And essentially what you would be looking for are physical locations that match up with maximum constructive interference. Okay, so yeah, if you have two different sources and you can control the volume of each of them, then you could find a spot where the sound perfectly cancels. But in real life or in like more practical scenarios, you're getting less than perfect maximum constructive, but not completely destructive interference. And then we had a question about 3 hertz in either direction from this last thought question. I'll share, hold on, I have to do it this way. I'll share again right here. We knew that the beat frequency was 3 beats per second, so that eliminated anything that wasn't 3 hertz in either direction. So if instead we had 6 beats per second, that would lead us to either A or D. But if we had like 5 beats per second, none of these frequencies would match up. It would need to be either 605 or 615. Okay, so let me go to the notes for the wave optics chapter. I mentioned that compared to first semester, we're going to jump around a little bit in terms of the chapter numbers. And now I'm second guessing myself. Is it 20? No, the newer edition is 33. Okay, so 33 for wave optics. All right, let's move this here. And the discussion that we were just having about interfering 3-dimensional waves, that kind of leads us perfectly into the beginning of our wave optics discussion. So it wasn't a coincidence, or it wasn't just a random choice that we mostly talked about sound wave examples in the end of the 17th chapter, because light waves are 3-dimensional. They do interfere with each other in a manner that's similar to sound waves, but we can observe it in a different fashion. So in other words, we don't like walk through the lab space, which has multiple light sources. We don't see bright and dim spots in the room the way that we would hypothetically be able to pick out louder and softer locations in the lab if we were just talking about sound waves. So we're delving a little bit deeper into the, we're still talking about just mechanical waves, waves that propagate through, let me refine that here. We are moving away from only talking about mechanical waves, and we're going to talk about light waves, which can go through either nothing, or they can go through any material that's at least partially transparent. So this involves light passing through like the glass. If you were to look out a window and see sunlight, this would be light passing through atmosphere. It could be light passing through water. There's not a requirement that there be a medium, but the type of waves that we're talking about now pass through different media, they're not simply going through a vacuum. So subdividing our models of light. We're going to introduce a new one today, and we're going to talk about the second one in more detail in our next chapter. We have the wave model and the ray model, where the wave model is representative of the fact that light has a lot of properties that we can relate to the waves that we worked with in the lab from last week from traveling waves, so the simulator. We could describe what's going on with a light wave in a manner that looks pretty similar to the description that we use for a transverse wave on a string. So we can find peaks, we can find troughs, as long as that light wave is moving through just one material and it's not crossing from one to another. We know that that wave is traveling at a consistent speed. We know that if that wave does cross from one material to another, the speed of that wave is going to change, but not its frequency. So in other words, if speed changes but frequency doesn't, that means that the wavelength also has to change. This is why if you were to shine like a red laser into a glass of water, you would never find a location where the laser looks like it changes from red to green, or if it would go from red to infrared, which you wouldn't be able to see. The color, which is the frequency, stays consistent the whole time. So what we are taking a look at here, and we're focusing on light waves for this discussion for reasons that'll become clear very shortly. We're going to take a look at how these waves can interfere with an opening of some sort. So this image here is one that was made from like a dish of liquid. Imagine that you have a speaker cone that you can connect to some device that would cause it to move back and forth with a consistent frequency. And if that cone is on the left-hand side here, the kind of lightest blue regions that we see would be the troughs. So the points in the dish or in the pool where the water level is higher than average. And the darker blue would be troughs where the water level is lower than average. So if our source is unshown, but it's here on the left-hand side and it's far enough away that the wave fronts that are approaching this little opening are essentially just straight lines as opposed to having curvature. Once this wave passes through the aperture, these wave fronts become distinctly circular. This is true for a large aperture, a small aperture, for high frequency plane waves being generated on the left or low frequency. And this is something that we can also relate to light waves. Now for the topic of the next chapter, here we've got a doorway, so like an opening. It's daylight on the opposite side, but it's dark on the interior of this building. And what we see here is a pretty well-defined line that is based on the shape and the size of the doorway. So this is something that you can also observe, or maybe just imagine if you have a door that's got like an old-fashioned keyhole in it. So one that's big enough that you could look through. You could shine a flashlight on that keyhole and produce a flashlight-shaped shadow or a flashlight-shaped light that is, what's the words that I want? That shows the same kind of distinction here, the separation between light and darkness. There's a term for this, like this line that separates light and darkness, you'll hear sometimes referred to as the terminator. It's a term that shows up in astronomy if you're like observing the moon and you want to observe a specific crater or some specific item on the moon's surface. If you look at the dividing line between light and dark on the moon's surface, you can examine the specifics or like the small details of that item a little bit more easily than if it were all in light, and obviously more easily than if that section of the moon's surface were all dark. The point here is that there's a sharp, well-defined line that determines, or that is the result of a light ray either making it through this doorway or not making it through the doorway. So what we don't see as readily is the spreading circular pattern that we saw on our previous slide here. because the sun is far enough away that we can assume that the light that is passing from one side of this doorway to the next is entering as an essentially plane wave, just like the water wave on the previous slide. So once we start talking about like ray tracing, prisms, mirrors, lenses in the next chapter, we're going to be working with the ray model. The bulk of, or really the entirety of this chapter is going to be devoted to the wave model. And then later on in the semester, once we get some field theory under our belt, we can talk about the photon model. And I'm sure we're all familiar with the light particle duality of light. Sometimes it makes sense to describe light as a wave that can propagate across space, kind of the same way that a water wave propagates on the surface of a pond. Sometimes it makes sense to think about that light as a ray, so something that would behave like a laser pointer and less like the lamp that is in my room and probably in your room. And then there are times where it makes more sense to model light as a particle that can undergo an elastic collision with matter, and something that we can model as, I always like to relate this back to like a bouncy super ball. If you had a handful of those and you flung them against the wall of whatever room you're in right now, what you would essentially be duplicating is how light particles interact with your walls, with your computer, with yourself, with everything that's in the room with you. And like I mentioned, we have to have a little bit more foundation on how electromagnetic waves work before we're ready for the photon model. If you think back to the first half of the traveling waves chapter, we talked about matter waves related to electromagnetic waves and mechanical waves. And we said that electromagnetic waves relied on the oscillation of an electric and magnetic field. The whole middle of our semester is talking about electric and magnetic fields. So once we're done with that, then we can come back to the photon model. But that's kind of like a roadmap of where we're going with this specific topic. And it kind of shows us how the conversations we're having now really early in the semester are going to impact or kind of dovetail with the ones that we're going to have at the end of the semester when we're all a few months smarter about this. Okay, so again, we're just talking about the wave model for this discussion here. And this little image is pretty much the same as this demonstration with the water wave that's passing through this aperture. And we have straight or like linear wavefronts that become curved. So we have just a single opening in this slit where this can be like a metal or paper or cardboard card that, or whose job is really just to take a diffuse light source and turn it into a narrower slit or like a narrower rectangle of light. But surprisingly, maybe counterintuitively, the image that you would collect on a screen would not just be a representation of the rectangular slit. So in other words, it's not going to be like the doorway. It's going to be more like the water wave that we saw. And instead of being able to like directly see these circular wavefronts, we would be able to confirm that this wave was curving, one, and two, interfering with itself by looking at the pattern that shows up on this screen. So we would see a pattern that's made up of bright spots and dark, or I should say bright like lines or bright regions and dark regions. And as we moved away from the midpoint of the pattern on the screen, sorry, let me get something so that my mouse will respond a little bit better. Okay, that's a little bit better. So if we were to trace from like the midpoint of this slit to the midpoint of the pattern on this screen, we have a bright rectangle of light, which kind of makes sense of, but these dark lines or these dark fringes, it's not just uniformly bright or uniformly dark, but a little bit of both. And believe it or not, single slit interference like this is a little bit more complicated than double slit interference. So this image on the left is legitimately a repeat from the previous slide. If you have two slits as opposed to just one, and you have a laser beam. We're using a laser beam here kind of for two reasons. One, because it is narrow and defined compared to a light bulb or anything like that. And two, it's made up of light that's just one wavelength, that's monochromatic, in other words. If we trace from the midpoint on the slit card, so where the light is physically blocked because none of it's actually passing through the card, it's just going through the slits on either side, what we would end up with is still a bright spot in the middle of this pattern, even though there's no direct straight line path to go from the midpoint of these two slits to the middle of the bright the middle of the bright fringe that's at the, or the bright like line that's at the center of this pattern. We would still see the pattern get dimmer near the edges, like we saw for the single slit diffraction example, but it's not as dramatic. And we would see that the width of the dark fringes, that doesn't really change as you get further away from the central maximum. So you get this kind of odd, probably surprising pattern for the double slit, and one that, again, is kind of difficult to guess, probably not how you would imagine a pattern from a single slit falling on a screen like this. But we're going to start with the double slit example because it's a little easier to understand, and then we're going to loop back to the single slit, I think, at the beginning of the second half of this chapter. So the takeaway here is that in both of these cases, we know that this light that's coming from the laser beam has to be interfering with something in order to produce these patterns. And it's more than just interacting with the slit. The light source is actually interfering with itself in between the slit and the screen. So for our double slit example, let's try to turn that light wave into something that looked like the water wave that we saw a few slides earlier. So you have some light source that's on the left side of this image. It's producing consistent light that just has one wavelength. So the laser is just one color. It's not like white light that's a combination of a lot of different wavelengths. It is, or the source is far enough away from this double slit that when these wavefronts make it to the left side of the aperture, they're essentially straight lines parallel to one another. But once they go through each of these individual apertures, these wavefronts are going to curve and bend. And what happens in the space between the slit and the screen is pretty similar to what we were just talking about in the previous chapter as it related to two loudspeakers that were spaced a certain separation away. We could relate that to the wavelength of the sound source itself. And we could find lines where we could count on either seeing perfectly destructive interference or maximum constructive interference. Now, we don't have the nodes matched out here, so we don't have the modes illustrated here. But we do know that anytime a maximum from one aperture crosses over a minimum from the other, we should expect perfectly destructive interference. So that's the justification for these dark lines that show up on the screen. You have a peak that matches a trough, they cancel out. The bright lines are going to be the opposite. So that's either peak and peak or trough and trough. But the point is that this is maximum constructive interference in this case. So you can trace one antinodal line from the midpoint between the two slits directly to the screen. And that's going to be our central maximum. We're going to use M's in a similar way to what we did in our standing wave conversation a bit earlier. So this would be M is equal to 0. So remember, for standing waves, we always start at M is equal to 1. But for light waves that are interfering with one another, there is a meaningful M is equal to 0 bright fringe. That's the term that we can apply to this. So that's the central maximum. Then as we work our way out, we're going to skip over this dark fringe for the time being, and then go straight to the next closest light fringe or bright fringe. So I have one above and one below. These are both M is equal to 1. Next out, I have 2m is equal to 2s, 2m is equal to 3s, and so on. And the broadness of the pattern that you would catch on a screen depends on the combination of the wavelength of light that you're using to produce the pattern and the separation between these two slits. It looks like it is, you should kind of think of this image on this slide as being a bird's eye view, so that you have like a rectangular screen or whiteboard or whatever that is collecting this horizontally oriented pattern. So you have m is equal to 0 in the middle, and then to the left and right, you have m is equal to 1, 2, 3, so on. So if we take a close look at what has to be happening here on the slit side of this experiment, as opposed to the screen side, which is what we were really focusing on in the last part. If you have some slit spacing lowercase d, and I should note for a double slit, the width of either individual slit is a lot less important than the spacing between the two slits. And we're always assuming that the slit width is the same for both, but that there's some fixed distance d apart from one another. So if we were to trace a light ray, that's what is being indicated by this purple arrow. And we're not meant to take these purple light rays as representative of a wavelength that actually matches up with purple light. That's just the color that Pearson used for these illustrations. So the wavelength is important to part of this discussion, but not really important to this specific part of the discussion. So all we need to really know is that there's a light ray that is centered on the midpoint of each one of these slits, and it's going to move or kind of propagate across the space to hit this, this screen. So in other words, just to roll backward a slide, we know for sure that this light is spreading out after it goes through the aperture. So what we're trying to capture is how much it spreads out. So we've got ray 1 up here, ray 2 down here at the bottom. And because of the fact that these light rays are centered at the midpoint of each slit and they are spreading out, there's going to be a really small difference in the distance that light ray 1 has to travel as opposed to light ray 2. And what we're looking for is this tiny right triangle. It's got a hypotenuse, that is the distance between the midpoint of each slit. It's got a like a sine component. One leg of this right triangle is going to be the sine component of this. Then the cosine component is going to be the line that connects the midpoint of one of these to the second light ray, but it's not going to go directly to the midpoint of the other slit. It's like taking a right triangle and then collapsing it so that its angle with the horizontal theta gets smaller and smaller, but doesn't actually disappear. So in other words, that right triangle has some non-zero height. And since we're concerned with the path length difference, the slight difference in the distance that this light ray has to travel to get to the screen, as opposed to the second light ray, we can call that tiny vertical leg of this right triangle delta R. So that's the hypotenuse d times the sine of theta. That triangle is similar to another one that we can see here on the right-hand side that is now centered on the midpoint right between these two slits. That's where this purple line that's on the right side of our screen would intersect with the slit card. That's what we are assuming is this line here right at the halfway point. The slits are so small relative to the physical size of the card that we can only see them in this inset, but they are present. So if we were to draw a right triangle that goes from the midpoint between the two slits up to one of the bright fringes, so one of those bright stripes, not the one that's dead center, but one that's displaced off to the side, then the vertical portion of this right triangle is going to be a way that we can communicate how far from the central maximum, which would be at 0, each additional bright fringe lands. And I want to point out that there are bright fringes that are below the 0 on this y-axis, but we're just taking a look at the positive ones for the sake of simplicity. So if the screen is some distance L away from the double slit, and we've just identified that this angle theta here has to be the same as our angle theta that's on the left-hand side, then L times the tangent of theta gives us the separation between the central maximum, the central maximum here that's at y is equal to 0, and then one of these bright fringes. It's going to happen at L tan theta, where theta is going to change for each different vertical position. And in other words, M is equal to 0 would have a theta of 0 because L and that perfectly horizontal antinodal line literally overlap. But for each higher order M value, theta is going to get bigger and bigger. So there's not one theta that applies to every bright fringe. So we'll have to introduce a subscript so that we can tell the difference between the angle theta for M is equal to 1 and the one for M is equal to 4. So there is a behavior here that's kind of similar to the one that we saw for determining how wavelengths, or really half wavelengths or quarter wavelengths, can fit onto a standing wave on a string that's got 2 fixed ends. So for 2 fixed ends, we could only fit half lambda on the string because we had to have nodes on either side. Here, each one of these angles theta sub m is going to be some integer multiple of this constant, this ratio, lambda over d. So we are assuming that we're just using one color laser and that we're just using one slit card so that the slit separation lowercase d doesn't change from one experiment to the next. Now for this angle here, there is some meaning to the theta sub 0 angle. It is just going to be 0 radian measured with respect to the horizontal. But for each higher level or higher order mode, it's going to be lambda times d multiplied by an integer. That's how we can figure out where these bright fringes are, these bright stripes that would show up on the screen. So since lambda over d is always going to be the same value, if we also assume that L stays fixed, so we don't change the separation between the slit card and the screen, but we just leave that constant, then we can predict what the y sub m values should be for each of these bright fringes. So in other words, so here, if we are just looking at one of these rays or one of these antinodal lines for this specific example, the next higher order one would be a little bit further out. So the vertical position on the scale would be a little bit bigger for a larger value of m. But lambda, L, D are all constants. So these two formulas put together let us either predict where a bright fringe should fall on a screen, so long as we know the separation between the slits, the wavelength of the light that we're working with, and the distance between the slit and the screen. Or we can measure a y sub m value directly, measure an L value, and like take a D and a lambda and figure out what each of these individual angles has to be. And that second description is closer to what we're going to do in the lab that we're going to complete next week. We're going to set up some either double slits or diffraction gratings. We're going to use laser pointers that have different color and different wavelength to, one, confirm the wavelength of the laser itself. And kind of funnily enough, some of the accepted values that are on the lasers that we're going to work with are like comically incorrect. They have the wrong units in one case. It says that the wavelengths are millimeters. That should be way too long for us, or the wavelength should be way too big for us to actually see. So there's actually some like experimental justification for getting an experimental measurement of the wavelength as opposed to just trusting what is on the packaging. Then what we're going to do is work with an unknown diffraction grating. So I'm going to define diffraction gratings in more detail coming up. But imagine that I gave you double slits, but I didn't tell you how far apart the slits were. I just gave you a wavelength, a screen, and like a meter stick, and asked you to figure out what that spacing had to be based on what the pattern looked like. That's kind of what we're going to do with multiple slits as opposed to only two. So let me see. We're still okay in the chat. Does anyone have a question that they want to ask on mic while we're paused for a second? Okay, interrupt me if you do have questions about anything. So that's description, or that the geometry that we just discussed, let us identify where the bright fringes are located. But as we see for the double slit pattern, the dark fringes are also evenly organized with respect to this central maximum, m is equal to 0. And a good way to think about it is to imagine that if not for these nodal lines, you would just have a pattern that is a wide swath of bright light. But it's kind of like these dark fringes being superimposed on top of that, that turns that pattern that's just one bright rectangle into a bunch of narrow, bright stripes or bright fringes that are separated by dark fringes. So instead of just y sub m, y prime is the notation that we would want to use to identify where dark fringes are as opposed to where light fringes are. And just to roll back a slide here, y sub m was an integer multiple of m times lambda L over D. To find the dark fringes, we want half integer multiples. So we can still start with m is equal to 0 because that's still meaningful in this discussion. But for m is equal to 1, what we're trying, or I should say, the dark fringe that would be like y sub 1 prime is the location of this fringe that's in between 0 and 1. And m is equal to 2 would tell us where the bright fringe that's between 2 and 1 is. So m is equal to 9 would give us the location of the bright fringe between 8 and 9. That's how that works. So you'll rarely need to keep track of both the dark fringes position, or the positions of the dark fringes, and the positions of the bright fringes. Really, when you start working on one of them, you get a pretty clear understanding of what the other one has to be doing. But technically, you can start with either bright or dark. And if you start with dark, you would want to use this relationship here. Look for the half integer multiples. Okay, so we have another example here, and I'm doing better than I thought I would in terms of time. So give me a second to break out a OneNote section for this new chapter. I'll go back in and plug in the text from the example problems once I get a break later on today, because I have a lecture that comes right after this one, so that's why I never have the time to upload things directly after. Okay. So I'm just going to build this into chapter 17 and then split it out later so that you don't have to watch me make a new OneNote section. Light from a sodium vapor lamp forms an interference pattern on a screen 1.8 meters from a double slit. The bright fringes in the pattern are 35 centimeters apart. If the light's wavelength is 589 nanometers, what is the slit separation? So let's switch back over and we'll take a crack at this one. Okay, so we should be able to share here. Okay, so I'll leave some room here so that I can plug the text of this problem back into this. So here is the scenario that we've got. We have a double slit over here. And actually, let me exaggerate this a little bit. What we're trying to find is the spacing between these two slits. So let's say that here to here is lowercase d. There's wavelength, or there's light of a known wavelength. So lambda is 589 nanometers. We're going to want this in meters immediately. So we can convert this into meters by recognizing that 1 nanometer is 1 billionth of a meter. So 10 to the minus 9 meter. And when you're dealing with visible wavelengths that are, this should be nanometers, not 589 meters. But when you're dealing with visible wavelengths that are hundreds of nanometers, 589 times 10 to the negative 9 meters is equal to 5.89 times 10 to the negative 7. So that negative 7 is going to recur when we're talking about wavelengths that are in this range. Okay, so we know that wavelength. We also know that the distance between the screen and the slit card is 1.8 meters. So that's L is equal to 1.8 meter. And we end up with a pattern that looks like this. And let me peek at that text one more time. The bright fringes in the pattern are 35 centimeters apart. So I'll use a new color for this. Here is where our M is equal to 0 bright fringe would show up, just from the midpoint between the two slits directly across to the screen without spreading out. But M is equal to 1 would show up in 2 places. I'm just going to worry about the upper one. So we have this right triangle in green. This angle would be theta 1. So we can use what we know about the physical separation between M0 and M1. Let me move this so that I can label this here as 35 centimeters. And we used this to show that 589 times 10 to the negative 9 meters is equal to 5.89 times 10 to the minus 7. Okay, so we know the horizontal leg of this right triangle. We were told the vertical leg. We can use that to figure out what theta 1 is. And we're going to be working in radian for this chapter, so don't forget to switch your calculator over. So the tangent of this angle, theta 1, is going to be opposite over adjacent. So the 35 centimeters, I'm going to convert that to meters over 1.8 meter. So theta 1 is going to be the inverse tangent of that ratio. And let's see what we get there. 0.35 over 1.8. We're going to end up with an angle theta 1 of 0.192 radian. Okay, so that is what we're going to need to go back and forth between our two expressions. I'll rewrite them here since you can't see both of my screens at the same time. We have theta sub m is equal to m times lambda over d, and we've got y sub m is equal to m times lambda times L over d. So we started off knowing that, let me make a new line for this. We started off knowing that y1 was equal to 0.35 meters. We just determined that theta 1 is equal to 0.192 radian. We know the wavelength, so we can use the upper equation to figure out what the slit spacing has to be. And really, we could have used the lower one as well. These are both going to lead us to exactly the same conclusion. But since I've already calculated what theta 1 is, I'm going to use the one next to the star. So if theta 1 is equal to 1 times the wavelength, which is 5.89 times 10 to the negative 7 meters, divided by the unknown slit spacing d, but I do know that theta 1 is 0.192 radian. That means that the slit spacing d is just going to be m times lambda over theta 1. And let's see what we get here. So 5.89 to 10 minus 7 divided by that. We have lowercase d is equal to 3.0669 times 10 to the negative 6. This is meters. So we're looking at two sig figs for this problem. So this is 3.1 times 10 to the negative 6 meters, or we can say 3.1 micrometers. And that's a very small separation, obviously, but an achievable one and a kind of realistic one for some of the devices that we're going to be working with next week. You've got some wiggle room as to what you can choose to verify your laser wavelengths. So it's not a given that all of us will work with double slits or all of us will work with diffraction gratings. I will say that I think it's a bit easier to work with diffraction gratings in that particular lab, but you will have some options to work with. All right, so let's see. We've got our last few minutes here. We have two example problems at the end of this chapter, or this half of the chapter, that we will definitely not make it all the way through. But let's switch back and talk about diffraction gratings. Okay, so let me share on this end now. Okay, so our slit separation was a little over 3 micrometers from example number 1. I referenced a diffraction grating a bit earlier in our discussion of wave optics, and didn't really talk about what it was yet, but now that we have a little bit of understanding of how double slits or how two slits can affect a single plane wave and cause it to interfere with itself in a way that you can capture on a screen, multiple slits will do something similar. So to say that another way, the behavior that we just looked at for double slits is not incredibly different than what you would see for 3 slits or 5, or maybe hundreds or thousands of slits, depending on the device that you're working with. So imagine a card, or more likely either a thin film or a sheet of glass that has a bunch of grooves etched into it. They're all separated from one another by or from their nearest neighbors by some consistent value lowercase d. So it's got the same meaning as the separation between the double slits that we saw in our previous problem, but now we can apply it to multiple adjacent pairs of slits or grooves. That means that if we were to take a look at any pair of adjacent rays to try to figure out what the path length difference would be, we would get the same answer over and over and over again. So this delta R would be d times sine phi, or excuse me, not phi, but theta. Each one of these rays would lead to just a single M value, or a single bright fringe, in other words. So we can say that if delta R is a certain value for some certain slit spacing or grating spacing lowercase d, then all of the rays that match up with that same path length difference are going to have the same theta value. So they're all going to go toward producing an M is equal to 1 bright fringe. Or we can find another group that all goes toward producing M is equal to 7 or whatever. So the relationship here that we can draw between like the spacing between the slits, the distance between the grating and the screen, and then the wavelength of the light that you're working with, these first two are pretty similar to what we saw for the double slit. But there's a new piece of information down here at the bottom in the third equation. So since we're dealing with not just two grooves, but multiple grooves, maybe, you know, hundreds of thousands in a certain, or well, I guess maybe about 1,000-ish for the gratings that we're going to be working with in lab. But per meter, we're looking at hundreds of thousands of them. If we know the number of lines or the number of grooves that fit into some certain unit length, the reciprocal is going to tell us the spacing between two adjacent grooves. So capital N here is always going to be the number of grooves or the number of lines per unit length. The reciprocal is going to give us the length per pair of lines. And it seems a little redundant, but I like to kind of use that language when we're first talking about diffraction gratings, so that when you get into the lab, it's a little bit clearer what or how lowercase d relates to capital N. So these images here, we'll start with the one on the left first. Imagine that you have a white light, so something that you know is actually made up of multiple wavelengths, so as much red as there is blue, roughly. If you were to shine that light source on a diffraction grating, the pattern that you would get looks like this here. So you have an M is equal to 0 bright fringe that, again, if you were to trace right across, it would hit dead center on this diffraction grating. Then you've got ones that are on either side, and then M is equal to 2 on either side. And again, depending on the relationship between the wavelength and the slit spacing D, you might be able to get higher order M values to fit on the whiteboards that we're going to work with in lab next week. The takeaway here, or what I want to point out, is that the spacing between 0 and 1 is not exactly the same as the spacing between 1 and 2. It wouldn't be the same as the spacing between 2 and 3, because we have a bunch of wavelengths of light that are all a part of this white light source that we're looking at here. If instead you switched to a laser pointer, which had essentially just one wavelength, or a very narrow range of wavelengths compared to a white light, what you would find is that the amount of spreading that you would see for long wavelength light is not equal to the amount of spreading that you would see for shorter wavelength light, even if everything else was the same. If it's the same grating, the same distance, the same room, so like the same atmosphere, the waves would be traveling at the same speed. There is a relationship between how much lower or shorter wavelength light spreads compared to longer wavelength light. So instead of like red and blue or red and violet, which is what we normally see or what we will frequently see when we're talking about the bounds of the visible spectrum, we have blue and violet, where we know that blue light has got a slightly longer wavelength than violet. So if we have a source here on the left, we would find that the shorter wavelength spreads out a little bit more, or excuse me, the longer wavelength spreads out a little bit more than the shorter wavelength does. So if you had like two lasers, a blue and a violet, or maybe a red and a green that you could set up together, you would see a pattern that looks kind of like this, where they all overlap each other here in the middle, so you get something that looks kind of whitish. But the further away you get from that m is equal to 0 bright fringe, the greater the separation would be between where the blue source hits the screen and where the violet source hits the screen. So I'll end on this idea here. This is the justification for like why you can see like a rainbow type pattern if you looked at the underside of a CD or a DVD. And it also ties into, or it's also something that we can see just in the natural world. For an example, this peacock feather. This is an example of some naturally occurring material that has properties that are similar to a diffraction grating, so that you see like some diffraction or something that kind of looks like iridescence when you look at a peacock feather. This is something that we can tie back to something being lined up in parallel lines, the something in this case being melanin. So when they are lined up, the result, so when when light interacts with these melanin rods, the result is not all that different from what happens when light interacts with a manufactured diffraction grating made out of glass or film or whatever. And then here on the left-hand side, this is how a different type of grating or a specific type of grating, a reflection grating, works. Instead of a flat surface that has grooves etched into it perpendicular, you can have some offset here so that a light source that, again, this purple is just meant to represent a white light source that's made up of reds, blues, and everything in between. When that light source strikes the surface of this reflection grating, some of it is going to, or I should say the red part is going to reflect at a different degree than the blue part, so that the light will actually kind of split up. So this is, again, pretty similar to what you see when you look at a CD's underside. You can see the difference between, or you see something that looks like a rainbow instead of a bunch of white light that's overlapping itself. The reason why that's visible is because the degree or like the broadness of the red part of that white light source is not the same as the broadness of the blue part. So they're not overlapping each other, but they're spread out a little bit. So you can see the difference between blue and violet and yellow and red and all of that. And we can start with this example problem at the beginning of our next lecture on Monday. So I have the lab for next week, the wave optics lab, already posted on Canvas. And this one that's coming up is going to be more formal than the ones that we've done thus far, and really more formal than any of the ones that we encountered in semester one, where I'm going to give you kind of a loose prompt. I'll ask you to prove or to collect data on the wavelengths of the lasers that we're working with, and then I'm going to ask you to identify a grating with an unknown number of lines, and then you can put it into a more formalized report. This is something that you can work on in groups if you want, or if you want to submit your own paper for just one grade, that's okay as well. But I just want to give you a heads up that the next one is going to be a little bit different than we've seen thus far, but by no means are we going to be doing this every time in second semester. We're going to go back to some labs that are more akin to the ones that we did for last week and this week. So this is just kind of an exercise or an opportunity for us to go a little bit deeper than we were able to in semester one. All right, let me log out of my extra account. I apologize, I'm a few minutes over. Do you have any last minute questions or concerns for me before we call it a day for this morning?